All right. So far when we're looking at vectors, we've looked at some vector operations. That is, we've added vectors, we've subtracted vectors, and we've multiplied vectors by a scalar, right? So meaning I'll take a vector, something like 2, 7, and I can multiply it by a scalar, a non-directional number. And to do this, I just kind of distribute. So 3 times 2 would be 6, 3 times 7 would be 21, okay? This is known as scalar multiplication, or it gives us a scalar product. Okay, product is the result of a multiplication. Okay, now I want to talk about something different. I want to talk about dot product. Okay, so dot product is sort of a way to multiply vectors. And I say sort of because there's really 2 different ways to multiply vectors. Well, there's 3 different ways. There's a scalar product, there's something called the dot product, there's also something called the cross product. We're not actually going to do the cross product in this class, but cross product gives us a vector as a result. Scalar product, multiplying a scalar times a vector, gives us a vector result. The dot product actually takes 2 vectors and gives us the result as a scalar. Okay, so the dot product takes 2 vectors, so 2 vectors are the input for the dot product, and the result is a scalar. That is just a number, okay? So good news and bad news with the dot product. The good news, dot product is pretty simple to do. The calculation for dot product is pretty straightforward. Bad news, understanding the dot product in terms of what is it and what is it showing us geometrically is a little trickier, okay? So we're gonna start just by straight up calculating the dot product. So in other words, if I have 2 vectors, let's say A, which equals 1, 3, and B, which equals, let's do this in 2 colors, that's more fun for me. And B, which equals -3, 5, okay? The dot product, which we symbolize with a dot, right? So A dotted with B. Okay. In order to do this, the calculation that we perform is we take our horizontal components and we multiply them together. So 1, so I'll have 1 times -3. So I'm multiplying our horizontal components together, and we add that to what we get when we multiply our vertical components together. So 3 times 5. Okay. So 1 times -3 is -3 plus 3 times 5, which is 15. -3 plus 15 is 12. So A dotted with B is equal to 12. Notice that I took 2 vectors and my output is just a scalar, just a number. Okay? So pretty straightforward to calculate. You multiply horizontal components and add that to the multiplication of vertical components. Okay? So again, let's just do a couple more examples. So this is dot product when we have our vectors in horizontal and vertical components. Okay? So let's try A equals -7, 1/2, and B equals -2, 1. Okay. So then if we do the dot product, A dotted with B, again, to calculate this, we multiply the horizontal components. So -7 times -2, added to, we multiply the vertical components. 1/2 times 1. Okay. -7 times -2 is 14. 1/2 times 1 is 1/2. 14 plus 1/2 is 14.5. Or let's see, 2 times 14, 20, 29 halves. Okay. All right. So not too challenging again to compute. We're just doing horizontal components multiplied together plus vertical components multiplied together. Okay. So again, this is our dot product. Now, what I want us to think about is we've done geometric interpretations of a lot of these things, right? So we've thought of addition as lining up our vectors tip to tail and looking at the resultant. We've thought of subtraction as kind of adding a negative. We've thought of scalar multiplication as kind of making copies of our vectors or cutting our vector into portions, okay? So what about dot product? What is the geometric interpretation of the dot product? So to get kind of a better understanding of this idea of projection when we're dealing with vectors and the meaning or the geometric interpretation of the dot product, here's two vectors, 3, 0, and 2, 2, okay? Now, I've got them at with the same initial point. 3, 0 means I'm going over 1, 2, 3 units horizontally and not up and down. 2, 2 means I'm going over 2 and up 2, okay? Now, this idea of projection, right? One way sort of to think about the projection is if I'm projecting this pink vector onto the orange vector, kind of colloquially what we think about is we think about, imagine that you had a sun up here casting light down, okay? This vector is going to cast a shadow, right? So it's going to cast a shadow. Oh, I'm such a bad drawer, right? But it's going to cast a shadow. So the shadow of the pink vector might be something like this, okay? The length of this shadow is what is given by the dot product, okay? Or we're projecting this pink vector onto this purple vector, and the dot product gives us that projection, okay? So in this case, if I do this pink vector dotted with V, okay, I'll have 2 times 3, 2 times 3 is 6, plus 2 times 0, which is 0. So I expect that projection to have magnitude of 6, okay? So one way that we can interpret the dot product is this idea of projection. Now, we're not really going to use that in our class, but I think it's useful to sort of think about the geometric interpretation of these things, okay? Now, the last thing that I want to think about for dot product algebraically, right, is the dot product commutative? That is, if I have two vectors, we'll call them U and V, okay, is U dotted with V the same thing as V dotted with U? Okay, is this commutative? Well, one easy way to think about this is let's try it. Let's see. So I'm going to say that U is the vector -1, 2. And we'll say that V is the vector, 3, 4. Okay? And we're going to try this both ways. So we're going to do -1, 2 dotted with 3, 4. And then we'll also try 3, 4 dotted with -1, 2. And again, our goal is to see if these are commutative. Okay? So, -1 times 3 is -3, plus 2 times 4, which is 8. -3 plus 8 is 5. So U dotted with V is 5. Let's look at V dotted with U. 3 times -1 is -3. 4 times 2 is 8. -3 plus 8, still 5. Okay? So it turns out this is commutative, and that really makes sense because think about the operations involved. Addition, which is commutative, and multiplication, also commutative. Okay? So this is dot product component-wise. Component-wise, when we do the dot product, right, we do horizontal components multiplied together plus vertical components multiplied together. Okay? But we don't always have vectors in their horizontal and vertical components, right? Sometimes we have vectors in terms of their magnitude and their direction. Okay, so here we have a vector with magnitude 3 and direction angle 330 degrees, and one with magnitude 4 and direction angle 45 degrees. So let's sketch these and see if we can think about what the dot product might be between them. Okay, so our first vector U is at 330 degrees, so I'm going to come all the way around here to 330 degrees, and it has magnitude 3. Vector V is at 45 degrees, and it has magnitude 4, so it's going to be a little bit longer. Okay. All right, so here's our two vectors. Okay. Now, if we're thinking about projection, right, so the dot product is a representation of a projection, or if I shine a light up here, how is the shadow of this vector going to cast along the path of this vector, right? Well, what things influence that? Well, the length of these vectors is clearly going to influence the shadow. And additionally, the angle between them is going to influence the shadow. So If I have a different angle, that's going to change the shadow, okay? So this kind of leads us to the other interpretation of a dot product. So if I'm going to dot U and V, okay, I can think of that as the magnitude of U times the magnitude of V times the cosine of the angle between them, okay? Now I've used theta for these angles, so just to kind of not confuse myself, I'm going to use alpha, okay? So this alpha is the angle between these two. So on our picture here, this would be angle alpha, okay? The angle between our two vectors. All right, so what does that mean? Well, can we figure out the angle between these two vectors if we know that our blue vector has angle 330 degrees and our orange vector has angle 45 degrees? Well, sure, I think we can, right? The measure of alpha is going to be 45 degrees plus this measure here, which will be 360 minus 330. So 45 degrees plus 30 degrees tells me that alpha is equal to 75 degrees. Okay, that's the angle measure between our two vectors. So if I want to calculate U dot V using this method, well, U, my magnitude of U is 3. My magnitude of V is 4, and then I'll do cosine of the angle between them. The angle between them is 75, okay? I'm gonna go ahead and just use my calculator and get a decimal approximation here. So I'll have 3 times 4 times cosine of 75, and that gives me approximately 3.1, okay? That tells me that my dot product is 3.1. So geometrically, what does that mean? Well, that means if I shine a light down here, the shadow of this is actually going to be slightly longer than this blue vector. The shadow would have magnitude of 3.1. Okay, so that's our kind of geometric interpretation of the dot product. Now, it doesn't really matter too much for what we're going to be doing in this class, but it does lead to one interesting fact. I can find my board eraser, which my children have clearly stolen. Okay, I want to think about one picture here, just to help us see one fact about dot products that we are interested in, okay? I want to imagine that we had two vectors again, okay? So some V and some U. And notice that I put these vectors so they are perpendicular to each other, okay? Now what happens if I have something perpendicular and I have a light shining from above? Is this going to cast a shadow if the light is directly above U? It's not. So what's going to be the projection of that shadow onto V? Well, there isn't one. There's going to be no shadow. So it seems like the dot product of two things that are perpendicular should be 0. Let's see if that makes sense. Okay? I'm going to give these vectors some magnitude. So let's say this vector has magnitude, it looks a little bit longer, we'll say 5. So this guy has magnitude 5. And this guy, U, we'll say has magnitude, I don't know, 4. Okay. Well, the angle between them, right, is 90 degrees. So using that dot product formula, U dot V equals magnitude of U times magnitude of V times cosine of the angle between them. I called it alpha before because I already had thetas running around. I'm going to use theta because that's the common angle thing. So what does this say? Well, this will be 4 magnitude of V times, magnitude of U times magnitude of V, 5 times cosine of 90. Well, what's cosine of 90? The cosine of 90 is 0. So this is 4 times 5 times 0, which is 0. Okay, now I want to see if this makes sense with our other interpretation of dot product. Remember, our other interpretation of dot product says if I have something in component form, I can multiply horizontal components and add that to the multiplication of the vertical component. Well, I think these will be pretty easy to put into components, right? If I think about the vertical component and the horizontal component of V, V only has a vertical component. The vertical component is 5, the horizontal component is 0. It doesn't go up or down. U on the other hand, I think about horizontal and vertical components of u. Well, u only has a vertical component. It doesn't go left or right, so its horizontal component is 0, its vertical component is 4. If I do the dot product of 0, 4 times 5, 0, I'll do 0 times 5, that's 0, plus 4 times 0, that's 0, which is 0. So 2 vectors are perpendicular, also known as orthogonal. It's a fancy way of saying perpendicular. If their dot product is 0, or if the dot product of 2 vectors is 0, they are perpendicular or orthogonal. Okay? So that's 2 interpretations of dot product. Okay? One is if we have vectors in component form, we multiply horizontal we multiply horizontal components and add those to the multiplication of vertical components. The other interpretation says if you know the magnitude of both vectors and the angle between them, then the dot product can be thought of as the magnitude of the vectors multiplied together times the cosine of the angle between them.